Hi everyone, so this is a follow-up to the introduction to chapter 14 video, tutorial 1. And I'll now be looking at some practice problems that make use of just the simple equations that were given for each of the different types of energy. And then towards the end of the video, we'll also look at power and efficiency as well. So we're going to start with question 14.7 on page 502. So this question states that block A in P14-7 has a mass of 15 kilograms and is pushed 3.4 meters up the slope by a force, P equals 130 newtons. Determine the work done on the block by A, force P, and B, the friction force. So I'm going to start by redrawing the figure that was shown. So a lot of these questions you're going to notice are pretty similar to the types of questions, at least these early ones, very similar to the questions that you saw in the last chapter. So we have block A on a slope, and it is being pushed up the slope with force P. We have an angle given here, so this is a rise over run 8 to 15, and also given is the coefficient of friction at mu equal to 0.15, so not unlike what we've seen before, as I mentioned. We also know that mass of A is equal to 15 kilograms. And it says that it's pushed up the slope by a force P, as shown there, but force P equal to 130 newtons. Now it is pushed up the slope, so it would be a good idea to include that distance, that being the starting point, going up to a spot that is 3.4 meters further up the slope. So as I mentioned, we want to find the following. So I'll write that out. Determine work done on block A by, there's two different forces here. We have force P, but there's also a frictional force, as we would have learned in the previous chapter. So the first thing to do to solve a problem like this is just how we would do it in the previous chapter. Let's redraw the block, and since it's on an angle, we're just going to draw it nice and upright, and then we'll adjust the forces by that angle. So I'm going to now show this. This is the vertical. Our force P then is acting at an angle. I'm going to give you that angle, and it is 28 degrees. If you're not sure how to calculate that, you can look at the questions from the previous chapter. So this force going down, I said there is a force going down. Of course, there's a force going down. That would actually be, I'm going to show it back on the figure up top here, and so this is weight, right? Weight is equal to mg. I didn't forget to add it, I just haven't put it in there. I started with the diagram. I just wanted to show you exactly where that's coming from. So this is W equal to mg, and if you want you can solve it right there. So that's 15 kilograms times 9.81 meters per second squared. And so W is 147 newtons. We also have that force P that would be acting horizontally in this figure, and that's P equal to 130 newtons. And since it would be moving to the left, we know that there would be an opposite force acting due to friction. And that force of friction is equal to, remember, mu, and then either N or Fn for your normal force. So we can actually solve part A. It's quite straightforward. So for part A, it wants to know what work is done on the block by force P. Well, this block moves to the left, and the force is acting to the left. And remember that the equation for work is capital U equal to force times the distance. But that force, remember that force has to be parallel to the direction of motion, the displacement. And it is in this case. So that's why this one is straightforward, because we can just take our 130 newtons, and we're going to multiply that by that distance, 3.4 meters. So U is equal to 442. You'd be left with Newton meters, but remember Newton meters is a joule. Okay. So that's the answer for part A. For part B, same equation, right? U is equal to F times S, but what are we putting in for F? So in the first one, I said that this F is P. That's what they wanted to know. So this F now is going to be the force of friction. Okay, so we need to put in the force of friction here. How would we determine that? Well, we know that there's a value for mu, so that's given. We need to know what the normal force is. So the normal force would be the weight, but the vertical component of that weight. Okay, so if we have, here's the vertical component, here's the horizontal component. So this would be the horizontal component, the vertical component would be W cosine 28 degrees. And the actual normal force then would be the only one acting opposite to that. So I could break this up like we did in the previous chapter, where I'd say the sum of the forces in the y is equal to 0, and our normal force, which would be going upwards here, the normal force would be equal to W cosine 28. So I could write that all out, but by now, if you've done enough of these practice problems, you should be able to recognize that clearly there's no other vertical forces, and so that normal force is just equal to W cosine 28. And so I can just put that directly into my equation. So that U is equal to, for the force of friction, 0.15 times W, which is 147 newtons, times cosine 28 degrees, times the distance now, which is 3.4 meters. And remember, it is parallel, right? Yes, it's to the left, the actual displacement, even though the force of friction is to the right, but it is parallel. It is in the same, that same plane. So U is equal to 0.15 times 147 times cosine 28 times 3.4. You should get 66.2 Newton meters, which ultimately is joules. So based on that, clearly there is more work being put in to push this block versus what is being put in to oppose that block through the force of friction. And that would make sense, because obviously if the force of friction was higher, then that block shouldn't be moving, right? So that does make sense. Okay, so let's move on to another problem. And just actually, before I do that, again, part B, I can break that up kind of like I did in the previous chapter, break it up even further. So if you're not sure how to do that, go back to the problems that we did before, and you're just doing the sum of the forces in the y. Okay, so let's go to 410 on page 503. So in this one we have a winch, and it's showing, so I'm just going to redraw this. Okay, so it's got a winch here. It's just a very simple diagram for this, and there is sort of a lever here, and we have a cable that goes around and down to a block that is 8 kilograms, and all this is just showing that it's how it's being held there. So we have a force P acting at the end of this lever. We have a distance here between the center of rotation and that force P. Okay, so it says the winch shown here lifts an 8 kilogram mass a height of 2 meters. So we can include that. So it goes from this point up 2 meters. Due to cable friction, the tension in the cable at the winch is 120 newtons. So another kind of way of showing that would be like this, right? There is a tension here, and that tension is equal to 120 newtons. So it just says, again, due to friction, the tension in the cable at the winch is 120 newtons. So determine the work done on the 8 kilogram mass for part A. So determine the work done on the 8 kilogram mass. Okay, so this is for part A. Determine the work done on the 8 kilogram mass. Okay, so well, we need to. We'll start with that one. So it says the work done on the 8 kilogram mass. Well, we do know it moves up 2 meters, so we know that that's the displacement. We also have a weight, and obviously then that weight is what is going to provide tension in that line. Okay, so that might be a little confusing because you're going to look at it and say, well, yeah, but we have a tension of 120 newtons. Yes, but that's also due to the friction in the line, and that's at the other body. So in this problem, there's actually, again, 2 different bodies. There's the 8 kilogram mass, that box, the block, whatever you want to call it, and then there's the actual winch. So what you would have to do is draw free body diagrams for each. So for part A, all we really care about is a free body diagram for that block. So if we draw that out, we know, again, so that's 8 kilograms. And so we have a weight here equal to mg, and we have tension in the line that opposes it, and that's it. We know that this is raised 2 meters. Okay, so when we look at part A, we're going to write out the equation. So U is equal to F times S. We want to know what the work is. Well, the force in this case would be, well, either the weight or the tension. They have to be equal to each other, right? So we can say that that is just W times S, which is equal to mg times S. So if I substitute in, we have 8 kilograms times 9.81 meters per second squared times our displacement of 2 meters. So U is equal to 157 joules. Okay. All right, next one's a little trickier. So for part B, want us to determine work done by the winch. Okay, so in this one again, it's just work, so U is equal to Fs. So it's always, whenever they're saying work, U is equal to Fs, it's just determining which one is which here. And actually, well, I say this one's a little more difficult. In fact, this one's might be a little bit easier. If we're just looking at the winch itself, you can draw the free body diagram for this one. And what you would have is, work done by the winch. So all that's happening is, okay, so here's the winch, and we know there is a tension, right? A tension in that line. And we've already said that that tension is equal to 120 newtons. When we lift that block up, that means we're lifting up 2 meters. That means that winch is pulling in that line, in that direction, parallel to T, right at the winch. And so this one is very simply just 120 newtons times that displacement of 2 meters. That's equal to 240 joules. Okay, so 2 different bodies, 2 different values. What we're really seeing is that part A, that really is the potential energy, right? You're lifting the object with a weight up a certain distance. And so there's 157 joules of potential energy. The work by the winch, on the other hand, it's a little bit higher. And why is that? Because we also have friction in there. So there's losses. And as a result, there's more work being done to move the same amount, right? So it's just in a different form of energy. Okay, last but not least, we have the force of P. So we want to determine the force of P on the handle of the winch if 9 revolutions were required. Okay, so this one's a little bit different. So I'm going to add in another page so we can see this a bit better. So for part C, we want to determine force P on handle if 9 revs, so revolutions, were required. Okay, well, let's turn our revolutions into our base units. So for displacement, theta is equal to 9 revs. I want to turn that into rads. So how do we convert that? Well, if we have revs on top, we need revs on bottom. So for every revolution, we have 2 pi rads. So that gives us 56.5 radians. Okay, so this is where this is a little bit trickier. We have a torque. You say, well, torque, hey, we haven't talked about that before. No, we haven't, but this is a very common term. Torque is just a distance, right? So that distance being a radius times an applied load. So just think of the mechanical advantage you get by torquing, applying a force on a wrench, for example, right? Where the wrench is turning a nut, you have a distance from the nut, from the center of the nut to where you're holding the wrench, and the force that you're applying is a force downwards. Well, you get that mechanical advantage based on the length of that wrench. So the longer the wrench, the more torque it's providing to turn that nut. Same idea here. So torque is just equal to T times R in this case. That torque is T times R. So that would be our tension times the radius. Now, the radius of this is the radius, it's not the 0.2 meters. That 0.2 meters would be the distance from the center of the winch to the force P. Okay, but what we really care about for this first part would actually be the radius from the center of that winch to where the torque is being applied, right? So that's the radius there. There's no radius given. So we're going to have to figure that out. How can we figure that out? Well, I'm going to state here where T is equal to, we've already stated it is 120 newtons. Think of our revolution. This is why we calculated the 56.5 rads, the total displacement. We have a conversion, an equation to convert between our angular displacement and linear displacement. Remember that? So that is S is equal to R theta. So if we put in our values here, we know we have a total linear displacement of 2 meters, and that's equal to R times 56.5 rads. So let me just explain that. What that's saying is we know that that block is moving up 2 meters. We also know that this winch has to turn 9 revolutions in order to get to that 2 meter displacement. And so the easy conversion between that, what is the radius of this winch? Well, we use this equation here. So now I can solve for R. R is equal to 0.035 meters. So now I can sub that into my equation for torque. So I have 120 newtons, and I multiply that by 0.035 meters. And so torque is equal to 4.3 Newton meters. And no, I'm not turning that into joules because this is a torque. Even though it has the same units, Newton meters, it's still a torque. It has nothing to do with work. Okay, so it asks, what's the force though? All we found is the torque. Well, that's because the torque then, so if I say what is force P, that's really what they want us to find here. Well, torque is also equal to, because we have 2 torques going on, right? If I go back, we have the tension times its radius, and that whole torque there needs to equal the torque being applied by P. So that would be P times 0.2 meters. So torque equal to P times 0.2 meters. Well, we already have a value for torque. We said that this is 4.3 Newton meters. That's equal to P times 0.2 meters. So if I divide both sides by 0.2, then I get roughly P equal to 21 newtons. And we're able to solve that problem. So that one, definitely a little bit more complicated. And wouldn't have been completely obvious, especially if you didn't remember our equation here over here for the conversion between linear and angular displacements. And also the key, of course, understanding that there is torque being applied. We hadn't really talked about that before, but there is a torque at the winch, and there's 2 of them going on here. We have the tension times the radius, and the force times its radius. And notice how in both cases, the radius is perpendicular to the force being applied. So that's really key. It's not parallel, it's always perpendicular. That force is perpendicular to the radius arm in order for it to be a torque. Okay, very, very important. Okay, so let's move on to something a little bit newer for us. We're going to look at 1414, and that's on page 503. So in 1414, it says a spring is initially compressed 50 millimeters by a force P. If P is increased 250 newtons, thereby causing a total spring compression of 150 millimeters, what is the spring constant? So this question is very easily miscalculated. This is where you'd have to go back to the equation that I talked about before. Remember, force is equal to K, K being the constant, the spring constants for a spring, times its displacement. Okay, but we're already starting with a displacement, and that displacement is from its uncompressed or free state. So here we're starting with already some compression, and then we're compressing it even further. So it's a little bit more complicated than just plugging numbers into that equation. So I'll show you what I'm talking about. We have 2 different states here. We have state 1, And it says that we have this spring, okay, and there is a load being applied to it. We're going to call that P1. We also know that it has an initial compression from its free state of 50 millimeters. Okay. We also have state number 2. It says that the spring is further compressed. Okay, so it's compressed even further now. And okay, so I'm going to apply. Remember, this certainly does change this force, and I'll look at that in a second. Now we have a total compression. So starting from the same amount here, a total compression from the same baseline of total spring compression of 150 millimeters. So again, I'll just restate what it says. It says a spring is initially compressed by 50 millimeters, which we see in for figure 1, by a force P. P is increased, so it's increased by 250 newtons. So that would be state 2 here. So what I could say is then P2 is just equal to P1 plus 250 newtons, right? Because it says it's increased by 250. So it had an initial P, we're calling that P1, and it's increased by 250 newtons. And this causes a total compression, so both from the same start point, 150 millimeters. What is the spring constant? So spring constant, remember this has to do with material type and number of coils in the spring and all sorts of different inputs to determine the spring constant. But that's often what we're looking for when we're doing a design. We need to figure out what the spring constant needs to be if you want a certain compression. Okay, so for the first one, what we can do is use our equation, right? And actually what I'm going to do is just move that over here, and I'm going to start with the first one. I'm saying that, remember that F is equal to Kx. Okay, force is equal to spring constant times the displacement. So given that, we can say then that that force F is really equal to P1 in this case, and we're going to multiply that by 50 millimeters because that's the initial compression. 50 millimeters, if you convert that into meters, would just be 0.05 meters. Okay, and we're multiplying that by K. So that's equation 1. Equation 2 would be very similar. I'm going to start with, F equals Kx, so it would be like saying P2 is equal to K times its X. So I just stated right to the left of this equation that P2 is equal to P1 plus 250 newtons. So let's use that instead. So P1 plus 250 newtons is equal to K times X. So I can either put Kx, doesn't matter what order. If I do X, it's 150 millimeters. So that really is just like saying 0.15 meters. It's at 150 millimeters times K. Okay, so what are we going to do? Well, we have really 2 equations and 2 unknowns. So it really depends on how you want to solve this here. One easy method would just be to take P1 here, and we can sub that directly into here. Okay, and if we do that, we should be able to solve this problem. So I'm going to take that 0.05 meters times K plus 250 newtons equal to 0.15 times K. So I'm going to have to collect my 2 Ks, put them on the same side, and then solve. And when you do that, in fact, if I just show that, I'll just show it like this. 250 newtons is equal to, I'm going to bring this over here. And so it's 0.15 K minus 0.05 K, which would actually just be 0.1 K. And so if I divide both sides by 0.1, then you end up with K is equal to 2,500 newtons. And that 0.1, I forgot to show it here and here, that's meters, so it's newtons per meter. There we go. Whoops. I want that to be my highlighter. Okay. All right, so there's 14 solved. As I said, it's an easy one to mess up. A lot of people will just take the equation F is equal to Kx and say, oh, okay, well, the displacement between the two is 150 minus 50 millimeters, so it's 100. And they just try to kind of solve it that way and get lost because they don't understand how you get two equations. So really try to break it up into parts, especially if they're talking about two different states here. Okay, very important. Okay, so let's jump along to a question 1490. So a big jump. This can be found on page, so a few pages down here. So page, still in highlighter, 518. Okay. And you can see it says applied problems for sections 14.9 of the textbook. So what that means is we're moving along to be talking about, we're going to be talking about power now. There is some gaps in here, so that's what I'm going to go back to, because those questions between the first few that I just showed and power and efficiency, they get quite a bit more complicated. So I just really wanted to go over all these basic equation type problems, and then we'll work our way up to those more complicated problems, okay? So in this one it says, again, we have a winch. This one is 2 feet in diameter and it lifts a 3,000 pound weight at 10 feet per second. What horsepower and torque must be supplied to the winch drum? So what we can do is, well, first I'm going to draw this. Okay, so there's our winch, and it says that the radius of the drum here is 1 foot. Okay, it also states that it is trying to lift a weight, and that weight is 3,000 pounds. Lastly, it doesn't give a force, but it does say it wants to lift it with a certain velocity. So that velocity is 10 feet per second. Okay. So I'll write out what they want us to determine. So we want to determine the horsepower and torque supplied to winch. Okay, so again, we're talking about torque. So torque is equal to, what did we say it was in our last problem? We said that there would be, the very first thing we said, torque was equal to tension times the radius of that drum. So of course, if there's 3,000 pounds that we're trying to lift upwards, okay, then we know that obviously the tension in the line here, that's T, and well, radius is already shown on there, so T times R. And in this case, it's not mass, be careful, we already have a weight. The weight is equal to 3,000 pounds. It's not 3,000 pounds times 32.2 feet per second squared. So we can easily just sub in then 3,000 pounds, because that tension equals 3,000 pounds, there's no other external forces, times the radius of 1 foot. And so our torque is simply 3,000 pound-feet. That's our torque. So we want to determine horsepower and torque. Well, we were able to just find the torque, so what it would be the horsepower. Horsepower is just power, right? So power is equal to, well, if you go back to the slides that I showed in the previous video, I said that there's a couple of different ways of solving for power. One of them would be force times velocity. Well, if we're dealing with torque here, then this would be equivalent to torque times instead an angular velocity. So that would be omega. So we can just take then our torque, which is 3,000 pound-feet, times an angular velocity. But oh, wait a second, we don't have an angular velocity, we only have a linear velocity. But remember, we can convert just like we did last time, except before we did that with displacement. Well, now we would be doing that with velocity. So V is equal to R times omega. So therefore, omega is equal to V over R, which is equal to 10 feet per second divided by a radius of 1 foot. So omega is equal to 10 rads per second. So we're going to take our 3,000 pounds and pound-feet, and we're going to multiply that by 10 rads per second. And remember, rads is kind of like a cheap way for looking at it would be to say that rads isn't really a unit. So what we would be left with is 30,000 pound-feet per second. And if you remember, we said that if we want to convert this from US customary units, pound-feet per second, when we're dealing with seconds, all we have to do is divide it by 550. And that was one of the conversions that I provided in a previous slide. So now P is equal to 54.5 horsepower. Okay. All right, so let's look at one more here. We're going to look at 1496, and this can be found on page 519. Okay, now this one includes power, but it also includes efficiency. So and this will end up covering pretty well all the equations. Now I didn't go over kinetic energy and specifically spring energy. We talked about spring forces, but you'll see how those come more into play as we go through some of the more complicated problems in our next video. So for 1496, it says a 75% efficient hoist is powered by a motor with 8 kilowatts of power. Determine the velocity at which it could lift 1 ton of material. So let's redraw this thing. Okay. And again, very similar to our last problem, it's a hoist. This is a common mechanical engineering type problem. Okay. And we're dealing with, what do we say, 1 ton, which is equivalent to 1,000 kilograms. You know, you'd have to make sure, I mean, that's 1 ton, T-O-N-N-E. If it was T-O-N, then that's typically 1,000 pounds. So you just have to be careful. And I'll be like on a, for example, the test that we'll be doing in the next few weeks, I will make that very, very clear. Okay, so we said that this thing lifts, it's lifting this weight, so we know that it is rotating with a certain velocity. We know that there is tension on this cable, right, pulling that up versus a weight acting downwards. So W is equal to mg, which is equal to 1,000 kilograms times 9.81 meters per second squared. And so the total weight here is 9,810 newtons. Okay, it says it's powered by a motor with an 8, so P is equal to 8 kilowatts, which is just equal to 8,000 watts, with an efficiency equal to 75%. It wants to determine the velocity. Okay, so that would be linear velocity at which this is being lifted, not the angular velocity of this winch or this hoist. What we're really looking for is that linear velocity of the weight being lifted. Okay, so the P value that is given here, it says it's powered by a motor with 8 kilowatts. Okay. Of output. Now, this sometimes it's a little bit confusing because it actually says it's powered by a motor with 8 kilowatts of outputs. So depending on how you read this will change which P value you are actually using. Okay, because it does say output, but you might read this and say, oh, it's being powered by 8 kilowatts. Okay, so it depends on how you read this. Okay, so I will try to make it very clear in any of the questions I ask, but for sure it can be quite ambiguous if you're not, especially if you're not really paying attention. This one isn't very clear to me because it says it's powered by a motor with 8 kilowatts, but it also says with 8 kilowatts of output. So you could say, well, that's the output. Do we even need the efficiency? Because we care about mechanical output. We don't care about mechanical or electrical input. So I'm going to assume what they're trying to say is that they are inputting 8,000 watts of electrical energy, and we're going to get out a certain amount of mechanical energy. So that P out then would obviously be less than the 8,000 watts being supplied. So we're going to multiply that 8,000 watts times 0.75, which would give us a total mechanical output of 6,000 watts. Okay. So power then is equal to, well, the base equation is U over T, so work over time, which if you broke that out would be force times displacement over time, or like I showed in the previous problem, it's just force times velocity. Okay, so if I rewrite that, force times velocity, in our case, what that force can be is just our torque times velocity, right? It wants us to determine the velocity. Well, do we have a power? Yeah, we have 6,000 watts. Do we have a tension? I don't know if I said torque earlier. If I did, that was my mistake, but a tension in the line? Yeah, it's equal to the weight, which is 9,810. Okay, so let's put those values in. So 6,000 watts is equal to the tension, which is 9,810 newtons, and that is being multiplied by velocity. So if I divide both sides by 9,810, then I get a velocity of 0.612 meters per second. And this one is a good example of saying, oh, wait a second, I'm dividing by my watts divided by newtons, so how am I getting meters per second? Well, if you're not sure, just break out the watts. Remember, watts is just newtons per meter per second. Okay, so if I'm dividing by my newtons times meters per second divided by newtons, my two newtons cancel out, and I'm left with meters per second for my final answer of 0.612 meters per second. Okay,